All right, cool. Let's get started with my talk. So I wanted to find a way to bridge a little bit the conversation between a lot of the stuff that we're talking on the sequencing side, on the validator side, as well as part of what the goal of all of this is, which is to actually improve the UX for a lot of users. So there's kind of like two different sides of the ecosystem that aren't necessarily talking to each other a lot, but are trying to solve the same thing. And I thought that I could maybe provide a little bit of context around how I'm thinking about the interface between these two problem spaces. My talk is going to be mostly about sort of the OneBalance view of the world. And we published this blog post on ETH Research that is sort of the source and maybe the inspiration for a lot of the theory and the exploration that happens in this talk. So I'll point you guys to that if you want to go a little bit more in depth. I'll sort of assume mostly pre-knowledge on this. So if there's any questions that things are not clear, yeah, feel free to go here and explore it a little bit more. So I'm going to focus on three things. One is the role of solvers in the chain abstraction thesis. Two is what I think a lot of people are trying to do, which is to help solvers manage risk. And then three, how the credible stack and credible accounts sort of fit into the picture. So maybe you guys saw the cake that was outside. Put your hand up if you had a piece and you tasted it. It's quite good. I do recommend it. The colors match as well, which is impressive. But I want to sort of reduce down the complexity of chain abstraction into the core thing that we're actually trying to do for users, which I think is somewhat simple. Is like, okay, what are all these pre-confirmations? What is 80% of what pre-confirmations are trying to achieve? It's, I would say, achieving permissionless atomic cross-chain swaps. Which is kind of like the holy grail of cross-chain composability, right? Mixed with what is probably 90% of the use case of smart contract blockchains, which is speculation over tail assets. And so what's involved in a permissionless atomic cross-chain swap? Well, basically, we want to be able to do a bridge, swap, and execute, where we're able to get assets on a different execution environment, have whatever swap required to be able to get the native gas there, and then do some execution. And the execution could be against a Uniswap pool. It could be any other type of execution. We want to have this property of having the best price, the best reliability, and the fastest speed. And we want to somehow not expose to the user the fact that there's a bridge, a different chain, or a different way to pay for gas. So I would say that that's sort of the holy grail of achieving chain abstraction, is to provide that user experience. And so the cake framework was something that we published earlier this year that essentially says a really good way to achieve this atomic execution in an asynchronous setting is to have solvers do a lot of that work on behalf of users. So introducing this third party, whether they're called solvers or relayers in an account abstraction, 4337 context, it would maybe be called a paymaster. You have a third party that's in charge of taking some user ops, some state transition requests, and actually putting it on chain and providing the execution. And so I sort of posit that short of having something like universal synchronous composability and every single roll-up and execution environment in the world being based and sharing the same validator set, you sort of need this layer to be able to provide the routing across all of these environments. So I'll just like quickly provide an idea and context on what the solver's job is. I think it can kind of be reduced down to two things. One is providing pricing. So whether it's aggregating all the liquidity that's available in all the different layers and then providing a quote for being able to access this liquidity as part of an RFQ or something like this, or simply routing. If you're across a bunch of different Uniswap pools and you're providing execution across all of it, you're kind of doing this to provide a price for the user to be able to execute. And the second thing is actually providing reliability on the execution. And so a lot of the stuff that we're talking about on the pre-conf side is being able to improve the reliability of the inclusion by saying that the validators are able to make commitments to the users to do this. The challenges when a solver is trying to do this, I would say are the following four. One is just risk management. You don't know what the future is, and you need to be able to price the future if you want to be able to provide guarantees to users today. 2, capital requirements. If you want to be able to execute on behalf of users on multiple different environments, you need to have capital on all those environments. 3 is access, so both access to maybe private pools of liquidity or also private pools of order flow that exists on all those different environments. And then 4 is speed. So you're always competing with other folks on speed when it comes to accessing either the order flow or the liquidity. So I would posit that a lot of the conversations that we've had today, since I'm presenting a model where the solvers are the one bringing things to the chain, are actually attempts at making the solver's job easier. If the solver is bringing all the operations to the chain on behalf of the users, the question is like, why? Why do we want to make the solver's job easier? I think that there's sort of 2 core reasons. One of them is that solvers have sort of become the big nodes of Ethereum, or like the master nodes of Ethereum, and we don't necessarily love that. We don't love the economies of scale that's involved with solvers providing and intermediating all the activity that happens on chain, and you want to find a way to flatten that power law distribution. And so if we remove part of the job of a solver, which is risk management, then perhaps we can also remove some of the pressures towards the centralization of it. So that's reason 1. I think reason 2 is to help solve this this trilemma. So this is a trilemma we also explore in the Cake research post. By the way, shout out to Ankit who authored it. But basically, there's this trilemma in any order flow system that's designed, whether it's an RFQ or a pure OFA, where solvers are sort of competing with each other to provide both a quote for execution and reliability of the execution on chain. But when you run an auction for these things, you have a winner's curse, and then you kind of have this problem where if you're providing the best price, sometimes you're overpaying for the value that you're paying the user, and you don't have enough left to be able to pay for the execution on chain. And so the way that all of these systems end up trying to resolve this is essentially introducing some kind of reputation score on the order flow system that says, okay, solvers need to meet some threshold of execution quality to be able to be part of the set of parties that have access to the order flow. And so this order flow trilemma introduces sort of this trade-off between price and speed when you want to remain permissionless. You can either say, okay, we're going to optimize for price, but maybe like 10%, 20% of the swaps won't execute, or you're going to optimize for reliability, but then the user price is going to pay an additional markup on their execution. So broadly, 2 reasons why it's good to help solvers manage risk. And I would like to put sort of 2 categories of approaches of managing this risk. The first one is validators providing commitments, or sequencers or block builders or whatever you want to name it. So basically downstream execution environment providing some commitments to the solvers to say, hey, you're going to get the execution that you want at this price, and look, I'm willing to guarantee it, and I'm willing to take the price risk on a change. And then the other type of ways to manage solver risk is from the account layer. And from the account is actually removing the risk of equivocation. Maybe a show of hands, so I have an idea of this. Who understands what I mean when I say the equivocation problem of accounts? Okay, actually, minority of the people. So maybe I'll touch on it quickly. So the equivocation problem is basically just that in distributed systems, you need to have a way for users to sign things, and you need to be able to sort of validate that those signatures are valid. If you have the signing happen outside of the global consensus, then you basically need to rely on something like a nonce to be able to say that a transaction is valid at a certain height. But a user can always sign 2 different transactions with 2 different nonces and essentially say that whichever lands on chain first is considered the valid one, right? But if you have an intermediary like a solver that's taking this signed message and bringing it to the chain, they can get griefed if you're able to sort of equivocate out of that request and send a different transaction on chain. And so one of the ways that you protect solvers here is that you remove the ability for users to equivocate out of their request using some external source of trust. Some people just use Ethereum mainnet for this, right? So you lock your state inside of an escrow on chain, and you're able to sort of avoid equivocation because it has a time lock on it. Okay, so I would sort of say that those are like two ways that we are sort of approaching minimizing solver risk or helping solvers manage their risk. So I would sort of propose what is a framework for thinking about these methods holistically. And also posit that a framework like this is required if we want to achieve sort of a seamless user experience in a cross-chain setting, have all this nice atomic execution on an asynchronous environment without requiring a lot of sort of fundamental changes to how everything works. So I call this framework the credible stack. And there's a QR code there to an article that sort of deep dives on it. But the main thing that's relevant to look at here is, okay, what are the sort of differences between this and how the world works today? So how the world works today, you sort of have, you could say that this is like a vertical MEV supply chain, right? You guys are going to be familiar with the users and the wallets, and then the solvers, and then you have sort of the chains and the block builders at the bottom here. What we're proposing here is that there's a way to, for the users to make commitments over the state of their accounts and issue what we call sort of resource locks. And these are commitments that solvers are able to trust and believe in and provide the execution on a cross-chain setting without necessarily requiring the user to do an execution on the source chain immediately. And then the solvers are also relying from the bottom on commitments coming from the chains, or the block builders on the chains, or the sequencers on the chain, to actually settle the user request. So with a credible stack like this, you're able to have execution across in a cross-domain setting, and have strong guarantees for the solver on the execution. What we get out of this is the concept of a credible account, which a credible account is just saying, okay, every state transition request is also coupled with a resource lock. So it's an amount of assets on a particular domain that is locked up pending some type of execution on a different domain. And you have a machine that's able to, or a secure computer that's able to secure that request. So these types of accounts, we've sort of presented a few different ways of building them. Like I mentioned, you could just use a chain to provide those commitments, or if you want to have faster execution, you can do a TE-based system. If you want to have sort of a more in-between solution, then you can use a crypto-economic solution using like threshold signing and MPC. All of these things are really just different ways of saying, an account can rely on some external system to co-sign transactions as part of the execution, such that solvers can trust the commitments that are being made by the users. So we have a big of a fellowship going on with a bunch of different teams that are interested in building on this credible stack, and they're working together to help make this a reality. And maybe the call to action for everyone here is, as we think about both improving the sequencing layer for rollups and for Ethereum, let's also couple it with a lot of the work that's happening on the application side with folks that are helping users actually provide this execution. And so if you're interested in working on these problems with all the nice people here, please come hang out with us and help us build it. Thank you. So I have 5 minutes for questions, and then we'll do the panel. Any questions? Yes.
Do you envision non-consumers also using these types of accounts, like searchers, etc.?
Hello. I think that, well, it depends on the construction. I think the beauty of these accounts is that it allows for two mutually distrusting parties to agree on something without relying on the global consensus. Now, the question is, like, for a solver, who's the counterparty that they need to agree with something on? Usually, the solvers will mostly want to be able to get the execution on chain, and so they want to agree with the validators, and so, you know, whatever, all the pre-commit stuff that we've been talking about is sort of useful for this. But yeah, is there sort of a different set of sort of bipartisan agreement that you think would benefit from it?
Yeah, I mean, thank you. Yeah, especially for like kind of mediating or coordinating mediums like MEV commit or maybe like shared sequences, et cetera, where, you know, it's not an end user oriented thing, but it's kind of a more solver searcher oriented thing. It's like, it sounds like they could have a OneBalance account there to then coordinate with those actors that you mentioned. So that, because those systems also have this kind of same global consensus / double spending problem to some degree.
Sorry, I missed the first part. So those systems being MEV commit or being what? Yeah,
or like shared sequences, or basically like kind of these L1.5s in some degree, right?
Right. You're asking why do those L1.5s use something like a credible account to be able to make those commitments?
No, I'm thinking that they could use it so that expands the use case beyond kind of the end consumer to also some of the, like, basically solvers could use it as well to do interactions with the execution service providers.
Right, with the, right. Perhaps, yeah, perhaps. I don't know, you know, I mean, a lot of the approaches to building pre-commits seem to take more like validator-oriented things, maybe like using restaking and these kinds of things. I mean, one of the questions I wanted to ask in the next panel is like, how are the pre-commits going to be enforced? And I think that relates on the same point.
Hi, Stephane. Thanks for this great presentation. Can you go back a few slides? I have a question related to resource lock you already mentioned. When you show, yeah. So for these resource locks, I'm interested how they are generated and how we can, as I can see, so someone make blocks on different chains, then we should wait for consensus, and then these external accounts could provide these locks across multiple chain, or what the pure mechanics not to achieve the double withdrawing funds at the same time. So how we can be ensured this resource lock was generated correctly and still on time on multiple chain? What the mechanics you really have here?
So I think for these, they would always originate from one trust environment. So let's say that you take a construction that's fully on-chain. So you would issue this resource lock essentially on chain A, and then anyone would be able to monitor chain A and say, okay, yes, these funds are credibly locked on this chain, and then do execution on chain B. You could have a different construction where like all of these are issued on a roll-up, right? And the roll-up is like holding all of these assets and then orchestrating execution on a bunch of other destination chains. So long as everyone can see that this roll-up has, you know, latest state, I think that's like where they would be able to tell the source of truth. So it depends on the account, where like I think each account will sort of provide its own source of truth on the state of this pending resource locks. Because your question is like, what if you have like resource locks issued on multiple chains? Is that it?
Yes, the question was who holds this information? Because here we have a real problem. If we are going to put this resource lock information on L1 and then reorgs happens, it means that you should roll back all transactions.
Correct.
Each based on this information. So
correct.
I just want to understand the mechanic, how you can achieve the 100% currency, or at least some insurance from the stakers who really prove that this resource lock has enough stake amount of money.
Yeah, like putting it inside of a rollup is like a good way to avoid this. But if you look at like the intent bridges, like they basically do this by just being optimistic about it, right? And so they'll say like, okay, you've locked your assets into this escrow on main chain. The solver is going to go and credit your account on the destination chain, and the solver is going to take over the risk of a reorg. If there's a reorg that happens, then the solver basically just gets griefed. But then the protocol has an insurance pool that's able to compensate the solver for that. That's sort of how those systems works today. Is they're kind of providing insurance against reorgs. But putting it inside of a rollup like helps avoid this, because like if your L1 reorgs your transaction out, you can just post it again, right? Yeah, for sure. Yeah. It's like it's funny, like the pre-conf stuff is like, it's also reorg insurance, just like paid up front, right? Like in a different way. But yeah, you're right. Anyone else? Okay, let's transition to the panel.
Yep.